In this module, you will learn about the third law of thermodynamics. We know that there is a change in entropy when we go from temperature T1 to temperature T2. This can be determined by integrating heat capacity at constant pressure over the temperature range divided by T. So, if we start at 0 Kelvin or absolute zero, then entropy at temperature T2 is equal to entropy at 0 Kelvin, that is, the sum of absolute entropy and integral of heat capacity at constant pressure over the range 0 to T2. Absolute zero is the lowest possible temperature, which is minus 273.15 degrees Celsius, 0 Kelvin, or minus 459 degrees Fahrenheit. Nernst made a suggestion based on a number of experimental studies. According to Nernst, the change in entropy for a chemical reaction approaches zero as the absolute temperature approaches zero. That is, the change in the entropy of the reactants going to the products as the temperature goes to absolute zero. Max Planck refined the statement. According to him, the entropy of a pure substance approaches zero at 0 Kelvin or at absolute zero. Hence, the third law of thermodynamics can also be stated as: every substance has a finite positive entropy, but in the case of a perfectly crystalline substance, the entropy may become zero at 0 Kelvin. In a perfect crystal, when the temperature reaches absolute zero, the constituent particles like the atoms, molecules and ions occupy their correct positions in a crystal lattice. Therefore, the substance attains the lowest energy possible. We can say that this particular state is of a perfect order, or it has zero disorder and so zero entropy. We can use the zero entropy of a substance at absolute zero as a reference point to calculate the entropy of the same substance in other states like solid, liquid and gaseous at various temperatures. We can calculate the entropy for a state of a substance by calculating the change in entropy for the process of conversion of the substance from the initial state to the present state. However, there are some substances that possess certain entropy even at absolute zero. This entropy is known as residual entropy. For example, the measured residual entropy of solid carbon monoxide is 5 joules per Kelvin per mole. The residual entropy is due to the very little energy difference between CO, 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 CO and CO, OC, OC, CO and other arrangements. So, the molecules adopt the orientations CO and OC at random in the solid. This gives rise to some disorder, also known as frozen disorder, and consequently residual entropy. You have now reached the end of this module. In this module, you learned that absolute zero is the lowest possible temperature, which is minus 273.15 degrees Celsius, 0 Kelvin, or minus 459 degrees Fahrenheit. Every substance has a finite positive entropy, but in the case of a perfectly crystalline substance, the entropy may become zero at 0 Kelvin. A perfect crystal approaches zero entropy at absolute zero or a temperature of 0 Kelvin. However, some crystals show a finite positive entropy at absolute zero, and this is called residual entropy.